So we'll start today with last details in 4.5, which was the solving for x section. All right, so log base 3 of x plus 78 minus log base 3 of x minus 2 equals 4. And log base 3 of x plus 78 minus log base 3 of x minus 2 equals log base 3 of 4. What's the big difference between those two problems, everyone?
There's a log.
Yeah, so one of them has logarithms on both sides, one of them just has logarithms on one side. Everyone see that? And that does change the way we solve the problem. Now, either one of these problems that you're solving, either one, you need to condense the left side to a single logarithm. And you need to do that whether or not it's a problem where you remove the logarithms or you rewrite it in exponential form. Either way, you need to do that. So that's going to be the quotient rule. So this is going to become x plus 78 over x minus 2 equals 4 log base 3 of x plus 78 over x minus 2 equals log base 3 of 4. Either way, you need to do that condensing, because you're not allowed, if you're going to try and solve for x, to have more than one logarithm on one side of the equation. But when you get to this point in the problem, it varies the way you finish it. Because this one, right here, you need to rewrite in exponential form. And what that actually means, since you're rewriting in exponential form, is it actually means that base of 3 matters. This one, you will remove the logarithms, and all that really mattered on this one was the bases match. It actually doesn't matter there was a base 3 on that other one, because we're just going to remove the logarithms. So this one, they could have been both base 10 or base E or base 50, and it would not have made a difference the way we solve the problem, because we're just going to get rid of them. This one, however, though, since we're going to rewrite in exponential form, it does matter that that's a 3, specifically. Because when we rewrite this one in exponential form, we have to write the base of 3, and what's the power going to be? 4 equals x plus 78 over x minus 2. Okay, then I guess we better do a little bit of math here. So 3 to the 4th is what? 81, okay, good. And then I'm going to multiply both sides by x minus 2 to get rid of the fraction. Sound okay to everyone? Okay, and that's going to give me 81x minus 162 equals x plus 78. Now, you might not like these numbers, but that's okay. We're still going to do what we normally do, and that is get everything with an x on one side and everything without an x on the other side so we can divide. So what I'm going to do is I'm going to subtract x from both sides, and I'm going to add 162 to both sides. And that's going to give me 80x equals 240. And it turns out when the dust settles, this one doesn't have a bad answer. What's 240 divided by 80? 3. We do need to check that answer in the original, but we can almost do this mentally once we've practiced doing it last time. If we check this in the original, here's what we have to do. We take this 3 right here, and we go like this. Is 3 plus 78 a positive number? Yes. Is 3 minus 2 a positive number? So we're okay. That's it. That's what I mean by checking it. So because 3 plus 8 and 3 minus 2 are both positive, this answer works. And you don't even really need to write that down. It's just really a mental game. I'm sort of putting that there. Oh, I'm sorry, 3 plus 78. I'm sorry. 3 plus 78 and 3 minus 2. You're really just checking for yourself to make sure that it works. I just wrote that there for your notes, so you kind of knew what my thinking was. So that's a problem where you rewrite it in exponential form, and you don't want to confuse that with the problem where you just remove the logarithms. And this one, we can remove the logarithms, and this one becomes x plus 78 over x minus 2 just equals 4, not 3 to the 4th. Because this one, we remove the logarithms, we don't rewrite in exponential form. We will still multiply both sides by x minus 2. And we will get x plus 78 equals 4x minus 8. We will still move things around. Add 8 to both sides. Subtract x from both sides. And get 86 equals 3x. And we will still divide to get x by itself. We get x equals 86 over 3. I like 86 over 3 just the way it is because it's an exact answer like that. Now, I don't know what that is exactly, everyone. 86 divided by 3, it's 20-something. But either way, 86 over 3 is a positive number. If you add 78 to that, are you going to get a positive number? And if you subtract 2 from it, are you going to get a positive number? Yeah, you are. So we check the answer. And for this one, we get, because 86 thirds plus 78 and 86 thirds minus 2 are both positive, this answer works. So I do these two problems side by side to remind you that this idea of removing the logarithms is a great way to solve problems when that is the way you're allowed to solve the problem. Otherwise, you don't want to do it. So two very similar looking problems, but one of them involved rewriting an exponential form, and the other one involved removing the logarithms. We okay with that, class? Make sure you practice those. All right, check this one out. We will introduce logarithms, either base 10 or base e, after we get 2 to the x by itself. That's a little multiplication dot in there, everyone. This is a problem that has x up in the power. We want to get the x down from the power. We get the x down from the power by using the power rule. We can't use the power rule until we have a logarithm. And we can't take a logarithm until we've isolated the base and the power. It sounds like a lot to do, but actually it's just a couple steps. If we want to get that 2 to the x by itself, I got to get that 6 and that negative 4 out of there. Does everyone agree with that? How do we get the 6 out of there? Subtract 6 from both sides. Then what do I do?
Add 4.
Not add 4.
To both sides?
Not add 4 to both sides, because what are we doing with negative 4 over here? We're multiplying. So what's the opposite of multiplying? Dividing. We got to divide both sides by negative 4. So it turned out this problem looked really evil, but it's actually not so bad. The only question I guess I have to ask myself now is, should I do a log base e of both sides, a log base 10 of both sides, or does it not matter? It actually does not matter at all. It does not matter at all. So at this point in the problem, you may either do a log base 10 of both sides, or you may do a log base e, a natural log of both sides. Either way, when you do that logarithm, you can use the power rule to bring the x down in front. And you divide. You do not divide just by the logarithmic symbol. You do not just divide by the number with the logarithm. You divide by the entire thing. So class, you must divide this one, both sides, by log 2. And this one, you must divide both sides by ln2. And whether you type log 5 divided by log 2 in your calculator, or natural log 5 divided by the natural log of 2 in your calculator, you will get the same decimal approximation as me.
2.321.
Can you give me 4 decimal places on that, please?
2.3219.
2.3219. Yeah, and I just do that because that's what I notice a lot of homework problems ask for, so that's what I want to get you doing for. That's it. All right. Cool so far? F of x equals 2 to the x does not have an x-intercept. It is an exponential function. It is an exponential function and has range 0 to infinity. So it is always above the x-axis. The graph of this is always above the x-axis. And if you wanted to get some points on this graph, because the domain is negative infinity to infinity, you could plug in anything you wanted. And what would be some good numbers to plug into this when we can plug in anything we want? What have we been using? Negative 2.
1, 0, 2, 1.
And 2 and 1. Very good, yes. And then we just got to remember our rules. Anything to the 0th power is what, class? 1. Anything to the first power? Itself. Anything to the negative 1 power? Itself flipped, squaring it, and flipping and squaring it. And then what we get is, I think this one will be better, so my graph doesn't get too busy looking. It's very big though. Don't need anything that big. We get a graph that looks like this. And then I'll go ahead and put 3.8 on here also just because I can. And I'm not claiming you doubted me, everyone. But can we all see from the picture that this thing does not ever touch the x-axis? So it has no x-intercept. In fact, it does have an asymptote. The reason I bring this up, everyone, is because this is something I actually brought up a while ago, was this graph. And I think I brought it up back when we were first doing section 4.2. And then one of the things I did with this graph was I shifted it down 3 units. I shifted it down 3 units. And when you shift it down 3 units, that's not going to impact the x values, but what you're going to do is you're going to subtract 3 from all the y values. So your new y values are going to become, whatever these are, minus 3. Well, that's a little bit annoying. So that's going to be negative 2 3/4, negative 2 1/2, negative 2, negative 1, 1, and 5. Boo. I wouldn't say I love that, but that's what they are. And then if I plot those points, let's see here, negative 2, negative 2 3/4. Yeah, this is not the easiest thing to do, everyone, but we can do it. Plug in 1, I get negative 1. Plug in 2, I get 1. That looks okay. Plug in 3, I get 5. You see, if the whole graph shifts down 3 units, the horizontal asymptote moves. And why do I bring this up? Because when I graphed this a couple weeks ago, I said to you, when we transform an exponential graph, it might change some of its features. And one of the features changes is that this now has something that the original didn't have. What does this one now have? It has an x-intercept. G of x equals 2x minus 3 has an x-intercept. And I don't expect you to remember every little thing I say, so I'm just going to remind you. What I told you was, back when I first did this back in section 4.2, I said, everyone, we can now see that it does have an x-intercept, but we don't know how to find that x-intercept. We do not know how to find it, but we do now. Because if we want to know where g of x equals 2x minus 3 has its x-intercept, then we set 2x minus 3 equal to 0 and solve for x. So if I set that equal to 0 and solve for x by first adding the 3 to both sides, do I in fact know how to solve that for x now? And we didn't know this back in 4.2. Why didn't we know this back in 4.2? Because what didn't we know about yet? Say again?
Solving for x.
Well, we knew about solving for x, but we didn't know about what sort of notation. What was new to us in this chapter, brand new? Starts with L, ends with algorithm. Logarithms. We did not know about logarithms back then. But now we do. So now, you see, in 4.2, we didn't have logarithms. So we couldn't get x down. But now, I can do a logarithm of both sides, bring down the x, divide both sides, and I can actually figure out where that x-intercept is. Now, maybe that's not the most amazing climax in math you were hoping for, like, ooh, I can find an x-intercept now. But it is kind of interesting to know that there were problems that we couldn't solve for x before, and now we suddenly have these brand new tools and we can solve for x in ways we couldn't before. As short as like a week or 2 weeks ago, we couldn't do this. But now we can. This one's one of those tricky ones to round to 4 decimal places where you have to bump up the 9 and then you have to bump up the 1 in the next place over. So round to 4 places, and this one, as I said, is one of those little tricky ones where you got to be careful that you're moving the right numbers in the right places. Does anyone know what this one ends up being? Well done. You know how to do it. Good job. That means, everyone, that it looks like our x-intercept is roughly at 1.5. Oh yeah, I guess it is. So I know that's not as cool as, like Star Wars. But mathematically, it's pretty cool that we can do that now. All right. And that, everyone, is going to pretty much bring us to the end of this section, but I have a couple closing statements to make. Don't invent rules. It is so easy to start making up your own rules because they seem to help you with a problem. It is very, very easy to think something like natural log of x plus natural log of x to the fourth is the same thing as natural log of x plus x to the fourth, but that's just not true. It sure looks like it should be true, but it's not true. And you'd be surprised how when you're doing your homework alone, you're not looking at your notes, or when you're taking the test, and you don't have your notes or your book in front of you, how easy it is to start making up stuff that you think is true, but it's not. In reality, what actually happens is if you have ln of x plus ln of x to the fourth, the product rule actually tells you that this is ln of x times x to the fourth, or ln of x to the fifth. Different. So this one right here was made up. This one right here is the product rule. So you got to make sure that you're actually using rules that are real and not making up your own rules. The solve for x problems in chapter 4 start with x in a power or x mixed into a logarithm. The solve for x problems in chapter 4 start with x in a power or x mixed into a logarithm. If x is in the power, see if the bases match or you can make them match. If x is in the power, see if you can make the bases match or if they match already. Otherwise, you will be taking the logarithm of both sides. So this is just a little recap of what we learned last time, everyone. There were no logarithms in it to begin with, but we had to take the logarithm of both sides to get that x down. We actually just saw that today again. If x is mixed in with logarithms, you will try to get rid of logarithms either by rewriting in exponential form or removing them. If x is mixed in with some logarithms and you're trying to solve for x, you're going to try and get rid of the logarithms, not bring them in. You're trying to get rid of them. And you're either going to do that by rewriting in exponential form or removing the logarithm. So one of the things I kind of tried to stress last time was people get confused when they're solving for x in these problems because it does seem counterintuitive. Because if there are no logarithms, you bring them in, and if there are logarithms, you're trying to get rid of them. So it's kind of like, what am I doing, Steve? Am I supposed to bring in logarithms or am I supposed to get rid of them? Well, it depends on the type of problem you're doing. That's why they're a bit tricky. And of course, this is just a recap, everyone. For more details, you'll need to look at your notes from last time. Finally, watch out for requests for an exact answer. Every now and then, you will do a problem where it does not ask for a decimal approximation, it wants an exact answer. Here's an example. Solve for x and give an exact answer in this problem. Solve for x and give an exact answer in this problem. Class, if x is mixed in with logarithms, you will try to get rid of the logarithm either by rewriting an exponential form or removing the logarithms. We have a logarithm on only one side of the equation. What do we do?
Divide by n 2.
Can't divide by n to 2 because this is all getting multiplied. This is a natural log of 2x right here, so we cannot divide. What do we do if we have one logarithm equals one number?
Move it and equal to the 0.
Exponential form. Sound familiar, everyone? One logarithm. If you have a single logarithm, and I don't care if it's natural log or what it is, equals a number, you rewrite in exponential form. That's a natural logarithm. So what's the base, everyone? E is the base. What's the power? 5. E to the 5th equals 2x. Now what is it time to do? Divide by 2. Now it's time to divide by 2. And we get x equals e to the 5th over 2. Do we reach for the calculator at this point? No. Why don't we reach for the calculator? Because it wants the exact answer. And this right here is the exact answer. If you plug e to the 5th in your calculator, as soon as you plug e in your calculator, you're going to start getting decimals, right? And that's going to be an approximation. So I'm not saying this is going to happen all the time in your homework, but I am saying it happens enough that you need to recognize when you read the instructions, and they should make it clear. That's their job to make it clear in the instructions. Or if it was on the test, that'd be my job to make it clear. We want an exact answer, which means just get x by itself and you're done. It is solve for x. That is the answer to this problem. And that's pretty much all I can tell you about section 4.5 without you just doing it on your own and seeing how it goes. Questions or comments? So, section 4.6 is the application section. But it is really all about one formula. It's really only about one formula, and it is given on the exam if needed. Just the formula, not how to use it. So just like the interest formulas that I told you I would give you on the test, that's absolutely true, I'll give them to you, but it's up to you to know how to use the interest formulas. And so I actually prepared something ahead of time, and this looks kind of long when you first see it, but I just wanted to have this very clearly in your notes. the formula that you're going to be using in this section. And so what this is, everyone, is this is the formula for exponential growth and decay. We'll look at this, and then we'll do a bunch of handwritten stuff like we usually do. The reason I wanted to put it up here to start with is because I wanted to show you all this formula is actually pretty much the same thing as the continuous compound interest formula. If you remember that, that formula looked like this. That was the PERT formula. Do you remember that one? And this formula is actually very, very similar to that in many ways. It just has a little bit more leeway on how we work with it. So it's still got a number in front, which we used to call P as our starting amount. And in this one, I always call that P sub 0. I think physicists have another name for it. I call it P sub 0. And that's still our starting amount. But the difference is in this section, we don't specifically always talk about money. So this could be some sort of bacteria that's growing in a dish, or it could be some sort of like people in a town, or bunnies living in the forest, or some radioactive substance. So we are not limited to just doing money in this section. So we'll still be given a starting amount. We just got to be aware that it's not always going to be dollars. Everyone okay with that? Same idea, right in front we put it. We still have an ending amount. After a certain amount of time has gone by, we end up with a certain amount. However, in this particular section, sometimes we let our population get bigger, and sometimes we let it get smaller. So depending on the type of the problem, we're going to see either the ending amount be bigger or smaller than it was before. Because we might have a city where a bunch of people are moving in, or we might have a city where a bunch of people are moving out. And the population's either growing or getting smaller. So with our interest problems, we always ended up with more at the end. But sometimes here, we will end up with less. It all depends on if they're talking about if we are doing growth or we're doing decay. Getting bigger or getting smaller. This whole thing just slide on me? Okay. There's an E in the formula, just like there was in the PERT formula. And remember, E is not a variable. You're not trying to figure out what number to plug in for E. E is E. E is a constant. It's roughly 2.718281828. E is just a number. You've got a button for it on your calculator. T is still time, everyone, but they're going to specify, are we talking about hours, minutes, years, weeks? They're going to tell us that. And we just need to pay attention to what they say. In the continuous compound interest formula, it was always years. Now it could be some other unit of time, but they have to tell us. That's their job to tell us. Probably the biggest difference, everyone, is we still have that percent that tells us how we're growing or getting smaller, and we still have to convert the percent into a decimal. The big difference is now we might have growth or decay, so it's possible that we will put in a negative number to show that our population is getting smaller. So we will still have a lot of the same things. The freedom is we're not just refined to money. We don't just have to do money anymore. We don't just have to do years anymore. And we can let things get bigger or smaller. But it's still the same basic formula. So we still have to convert to a decimal. 3% would still be 0.03, but that's if it says growth. If it says decay, then we still make the decimal, we just make it smaller. And this is what we're doing today, everyone, for the rest of the day today, so we get plenty of time to practice this. We will get used to this, and it'll be fine. What usually happens in these problems is we are given three things. So they will give us 3 of the 4 values listed above, and we must figure out the 4th. That's what's going to happen, everyone. They're going to give us 3 of those things in the problem. They're either going to tell us, the starting amount and the ending amount and the time, and we have to figure out the percent growth or decay rate, or they'll give us the starting amount, how it's growing, how much time we have, and we'll figure out how much there is at the end. They give us 3, we come up with the 4th. That's what we're going to be doing in this section. All right. Let's do some basic setups. Basic setup for how to use this formula. So we got P of t equals P sub 0 e to the kt. And we see this. We start with 100 bunnies. We have a growth rate of 1.6%. Give the function p of t with t as the variable. All right. This is just getting used to how this equation works. P of t equals P sub 0 e to the kt. What are they telling me in this little paragraph here? What am I being given? What values am I being given?
You start with 100 bunnies.
I start with 100 bunnies, so I'm being told that P sub 0 equals 100. Everyone dig that? What else am I being told?
What's the 0?
What's that?
The 0, the one in the bottom?
That one right there? It's just a notation. It's what it is it kind of is notation that means starting population at time 0. It's part of the variable. So the P and the little 0 go together. That cool?
Yep.
What else do they tell us? The growth rate. And that's good. It's a growth rate. So they tell us K is equal to 0.016. Note I did 2 things. It's positive because it's growth, and I moved decimal to make it into I made it a decimal instead of a percent. So what they were looking for on this one was this function. Give the function p of t with t as the variable. P of t equals 100 e to the 0.06 t. Now what I can do is I can plug in any amount of time and it will tell me how many bunnies I have. What are we doing right now? I'm not solving this. I'm not doing anything with that right now. I'm learning how to interpret what they say to me so I can write an equation. We start with 1,000 grams of a radioactive substance. It has a decay rate of 13%. Give P of t with variable t. How much do I start with of this radioactive substance? 1,000 grams, so I put 1,000 here. E is just E. What do I write for K?
0.13.
Close.
Negative.
No, my bad. Negative.
That's all right. Negative 0.13. Why do you know it's negative?
Decay rate.
Because it says decay. Because the problem says decay, that's how you know to make it negative. That's the trick. All right. So, we ready to try a couple of these? We ready to do some work with this?
Oh, this is the definition of K.
What's that?
The definition of K.
One more time.
The definition of K.
Oh, yeah. K is the growth or decay rate. It's a percent that you convert into a decimal. It'll be positive for growth and negative for decay. We solid with that? All right, very cool. All right. So, let's just do a problem like this. A town starts with a population of 2,000. You have a question, gang? You okay? Okay. Starts with a population of 2,000. And the population grows at a rate of 4.2% per year. Find the population after 5 years, after 20 years. So we're going to build an equation, everyone. I'll get us started. P of t. What's our starting population? 2,000. Trick question, what do I put in for E? E, because E is just E. Everyone agree with that? It's not a variable that we're supposed to put in something for. It is just E. And then the power on that, that's where we need to put in our growth or decay rate. Now this is grow,
4.2.
but we don't put in 4.2 because what do we have to do? We got to convert it into a decimal. So remember, 4.2% actually converts to K equals 0.042. All right, that's our equation that we're going to use. What do we do with it now? Plug in 5, and we'll look for an answer. And we'll plug in 20. Now, this particular problem is about people in a town. And because I am not a disgusting person, we're going to round to the nearest person. I will not have any fractions of people in my town. So everyone, what we're going to do is on your calculator, you got to figure out how to plug that in there. You got to figure out how to plug that in there. And this is the kind of thing that if you are not getting the correct answer, it's great to either talk to Rachel or myself about it, because we would be so happy to help you do this on your calculator. I can't speak for Rachel, but I'd be so happy that I would giggle. Anyone got 5 years for me? Round to the nearest person? Yeah, what do you think?
2,467.
Great.
Equals.
2,467. Well played.
0.356.
And why? No, stop that. No, I will have no fractions of people in my town. You're not to have point decimal people in my town. Disgusting.
Just have a leg.
No, there'll be no legs in my town. There'll be no elbows. All right, everyone. After 20 years, round it to the nearest person. It's not the nearest fraction of a person. How many people do we have? Who's got it? 20 years? Someone got it?
Is it
Yeah.
4,633?
4,633. You got it. Well done. All right, class. Now, when you're doing this on your calculator, it's a matter of using your parentheses correctly. So on most calculators, you can kind of see what you're typing in. So what you want to do is you want to do 2,000, and then when you hit your E button, it will prompt you for a power, with a parenthesis probably, and you want to make sure that you put that power in its own set of parentheses, like that. That's how you make sure you get the right answer. Okay, let's do a decay problem. Let's do a decay problem. All right. A radioactive substance has a decay rate of 2.41% per year. And we start with 100 grams. From just that, can you write an equation that we can use for this?
Yes.
Okay, go ahead and write an equation for me with t as the variable. Go ahead and write an equation for me with t as the variable. I just saw the time, everyone. We'll do this one, then we'll take our break. Sorry, I got so excited I kept on going. All right, so what number goes up here? Point?
Zero.
0.0241. And does it need to be positive or negative? It's got to be negative. How do I know it's negative? It's not a mystery.
Decay.
It's because they tell me it's a decay rate. That's how I know it's negative. And whether it's decay or growth, they're going to give you that percent. You got to move the decimal over 2 places. And then we drop the t in here. All right, now this one I'm going to throw you a small curveball, but I'm betting you're all so clever you'll spot it. How much do we have to 2 decimal places after 3 years, 18 months, 60 months? How much do we have after 3 years, 18 months, and 60 months? And a little warning to everyone, decay means that P of t will be less than P of 0. We're going to go down. We're going to have less.
Is this town or
1 second.
radioactive material?
What are we getting for 3 years, everyone?
93.025.
The 2 decimal places on this sucker, so we'll go, that's a good answer, we'll go with 93.03. What are the units on that? Did it tell us in the problem what the units are? Yeah, that's going to be grams. How are we doing, gang? Are we getting that 93.03? Working out okay? Now, I took the liberty of making a mistake up here. What's my mistake?
You put 18.
I put 18. What's wrong with 18? It says 18 right here.
It's 18 months, not years.
That's 18 months. So what happens, everyone, is both 18 months and 60 months must be converted into what?
Years.
Years before we can plug them in there. This problem is designed for years. Why do I know it's designed for years? Because it says right up here, my decay rate is 2.41% per year. So that tells me that I need to convert these to years. Now, fortunately, I picked ones that I thought we could convert pretty easily. 18 months is how many years? 1.5 or 1.5. Very good. 60 months is how many years? 5. So if you plug in 18 or 60, you're not going to get the right answer because you're doing 18 years and 60 years. This equation is designed to take years only. So we got to convert and do P of 1.5 and P of 5. I'll take 1.5 first to 2 decimal places, whoever gets it. I did 96.45. Can you check your rounding on that?
4 or 5.
Okay, cool.
Keep an eye.
I wasn't picking on you. I did it right before class, so I just want to make sure I did it right. And how about after 5 years?
88.65.
88.65. If you got these answers on your calculator and you're all set, go ahead and take a break till 11:37. If you want to stick around for a minute and ask for help on your calculator, I'll be happy to help you. 11:37, everyone come back, we'll do some more math.
Since it was only asking for 2 decimal places, you go on 7 to 5. In the question, yeah, right there, it says at the top.
So 2 big questions that come up a lot when we're working with these growth and decay problems. There's one for growth, one for decay, and the big growth question is, how long does it take for the population to double in size, which is called doubling time, some of you may have heard that before. And for decay, how long does it take the population to reduce to 1/2 its size? That's called half-life, which some of you may have heard before, especially if you've taken a chemistry class. So these are the 2 questions we're going to kind of focus on answering for the next bit of this lecture. What's interesting about this is you don't need to know how much the starting amount is to figure doubling time or half-life. And that disturbs some people, everyone, that you don't need to know how much you start with to do either one of these things. So I'm going to demonstrate that to you because it's not my goal to confuse you. But that's what makes this particularly fascinating. And let me show you why. A town has a population with a growth rate of 2.6% per year. How many years for the population to double? Now, if you've never seen a problem like this before, it looks like it's not giving you enough information to answer the question. The first time I saw one of these, I was like, that's not telling me enough. The only thing it's telling me is the percent. And there's a lot going on with this formula. But then you start thinking about it, and you think about what it's asking. Well, we're going to use this equation right here. And they're asking me the question, how many years? And when I read that how many years, what that makes me realize is that I'm going to try and solve for t. My answer will be a length of time. Does everyone see that? That my answer is going to be a length of time? If they're asking how many years, my answer is not going to be what the population of the town is or what the growth rate is. It's going to be, it takes this many years. And the only thing up here that gives a time is t. But I'm like, if that's what I'm looking for, and I know what k is, they tell me what k is. K is equal to positive 0.026. But they're not giving me p of t or p sub 0. But here's the idea, everyone. Let's say that we started with 100 people. If we start with 100 people, then we're trying to figure out how long it takes to get to how many people? 200.
So you can basically plug in whatever number you want for the starting.
You can plug in whatever number you want for the starting. Because everyone, if this was 1,000, we'd be trying to see how long it took to get to what? 2,000. And what happens, everyone, is if you plug these numbers in there, if you plug those numbers in there, 200 is the ending, 100 is the starting, or 2,000 as the ending and 1,000 as the starting, or even if you did 630 and 1,260, I don't know why you'd do that, and you're trying to solve that for t, the first thing you're going to do is you're going to divide both sides by that number in front of e to move it to the other side. Does everyone see that? And what's 200 divided by 100? Sorry, careful. 200 divided by 100? 2. What's 2,000 divided by 1,000? 2. What's 1260 divided by 630? 2. So no matter what your starting population was and what your ending population was, if you divide to isolate E and its power, you're going to end up with 2 equals E to that power. Regardless of what your starting population is, your ending population is twice as much. So you're always going to get a 2 over here. Question?
Why is it a negative if it's a growth rate?
Yeah, why would that be negative? That doesn't make any sense. It's almost like your math teacher made a mistake. Let's get rid of those minuses right now. Goodbye, 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 goodbye. You should have asked me if I had a question. Thank you very much before I got too far. Okay. Don't let that take away from what I'm telling you about doubling time. 2 over here. Whether we started with 1,000,000 or we started with 1,000,000,000, whatever number we put on the other side is twice that, so when we divide, we end up with a 2 over there. Now, because we've taken this class and because we did section 4.5, we know how to solve for a variable that's up in the exponent. But since the base in 4.6 is always E, we should use ln, not log. Even if you're a big fan of the log base 10, we should use ln because that's the base that's in there. And if you ever take ln of e to a power, because you have a base match, it simplifies to that power. So the right-hand side of that equation will simplify to what? Yes, it will simplify to 0.026t. How do we solve for t? What do we do?
Multiply by 100.
We don't have to do that. What would be a little faster? Since we're going to reach for the calculator eventually anyway, what we might as well do? Just divide by that decimal. I understand what you're saying to get rid of the decimals, but since this is our last step anyway, we don't really need to do that. And this should give us some approximation in years. I rounded to the nearest 2 decimal places, nearest hundredth on this one. Nearest hundredth. How long does it take the population to double?
What I got.
What'd you get?
Oh, well, I did it differently, but I was just plugging in numbers for the time, and I rounded to 26.7. This is what I would got.
I'll go 26.66. I'll do 2 decimal places, but good job.
Yeah, 26.66.
Okay. Now, class, that's how we figured out the doubling time. Now, this took a little while. This took a little while to do, but I'll tell you. I want you to look at the very last thing we did here. And think about where that came from. Why is there a 2 up there? Because the question was asking for what?
Doubling time.
Doubling time. So, the reason that we had a 2 was because it said doubling time. Where did this 0.026 come from?
That's the growth rate.
Yeah, not decay. I wrote it as decay. I wrote the negatives. That was my bad. But in this one, it was a growth rate. So, yeah, that was my mistake. This one is the growth rate, so it's right there. So we could actually even say that this right here is just k as a decimal, not as a percent. The point is this, everyone. Doubling time is an important question, but you don't actually need to go through all this work each time. If someone asks you for a doubling time, all you need to do is the natural log of 2 divided by your growth rate, and you win. Isn't that awesome? Look at this, everyone. Look at this. Oops.
So the equation for a doubling time would be 2 equals EKT, E to the key KT?
T equals ln of 2 over K. I'll write that in a second. Bacteria grows in a lab at a rate of 8.3% per hour. How long does it take for it to double? We do not need to go through a whole procedure. We're going to use what we learned on the previous problem. First of all, because this is saying doubling time, we're going to write ln of 2. Because it gives us this right here, I'm going to write 0.083. That's all I need to do for doubling time. I don't need to go through the whole process. It's this quick. What it actually is, everyone, is doubling time is going to be T equals ln of 2 over K. You still got to convert it into a decimal. So we do ln of 2 over 0.083, and we're going to figure out how much bacteria, we're going to figure out how long it takes for the amount of bacteria to double.
8.35.
Great. Do me a favor. Read the question again and tell me what I should put on that. 8.35 hours. Good.
So I can do so fast just when they ask for a double.
Yeah, isn't that cool? How about this? How about this? Check it out, gang. I want you to just make a conclusion on your own. Everyone just make this conclusion on your own, see if it works for you.
This equation.
Everyone see if you can just figure out arbitrarily on your own how long it would take for it to triple. I bet you can do this.
Just the,
I'm not even going to tell you, and no one tell anyone else. Let everyone else feel proud of themselves for doing it. Who's got it? 13.24.
Or
24. Did anyone else get 13.24? What'd you do?
Use 3 instead of 2.
You just used ln of 3 instead. Awesome. This one's kind of cool. Everyone do quadruple. Don't worry, I am going somewhere with this.
Score.
Someone who hasn't had a chance yet wants to show off their calculator skills. You want to tell me?
16.70.
What'd you get?
16.70.
All right. How did you do it?
Use N4.
ln of 4? Did anyone do it a different way?
I just doubled the answer for the first one.
Well done. If it's quadrupling, that's double the doubling time. And that works also. Isn't that awesome? Yes, well done. Glad you saw that. Yeah. Double the doubling time. If you don't believe that that works, then you just multiply that number by 2 and you'll see it works. Now, occasionally that gives you a slightly different answer, and that's because of a rounding error, not because the numbers don't work. So if you realize that you got to, like, if when you doubled this in your calculator, you ended up with like 16.71 or something like that, that can happen because of a rounding error. But in general, that's going to work. So we can do tripling time, quadrupling time, we can do whatever we want. All right. Pretty cool, right? I think so. Let's do this one. Let's do this one. We have a radioactive substance with a decay rate of, I don't think I did this one yet. No, well, either way. 2.41% per year. Give the half-life. Half-life means how long we're down to 1/2 the population. Now, everyone, if doubling time meant that we used ln of 2, what do you think we're going to use for half-life?
Divide by 2.
ln of 1/2 or ln of 0.5. Why? Because what happens is, if you're doing a half-life, and you have a starting amount and an ending amount, whatever you pick to start with, you are ending with half that. Everyone hip to that? So when you set up your equation, and you write 100 equals 50 e to the negative 0.0241 t. Yeah, we used this one before, but we didn't do the half-life with it. The first thing you're going to do is divide both sides. Shoot. I'm winning today. We start with 100, we end with 50. The first thing you're going to do is do what, everyone? Divide by 100. And if you divide by 100, you're going to get 1/2 over there. So, this is what we use for a half-life. Now be careful, because to do the half-life, you need to do ln of 1/2 divided by k. And k is a negative decimal because we're doing decay. So when you set this up, you need to do ln of 1/2 divided by negative 0.0241.
Equal 28.67.
Say it again, please.
28.76.
Good. Little tip for everyone, no matter what you do, you should never get negative time. If you say something's going to happen in -4 years or -12 hours, then you made a mistake with your sign somewhere. You're using a wrong number, you forgot to put a negative on your K, or you put a negative on your K when you weren't supposed to. So make sure you never get a negative amount of time. It's not a bizarre problem. It's incorrect, unfortunately. That is how we do a half-life. So, doubling time, ln of 2 over k. Half-life, ln of 1/2 over k. K is a positive decimal. K is a negative decimal. The thing that throws people off on these half-life problems is when they mix it up a little bit. Because sometimes, rather than asking for a half-life, they'll ask a question like this. Just a reminder, our substance has decay rate of 2.41% per year. And you get a question that looks like this. How long until 20% of the original amount remains. So they're not just asking for the half-life, they're asking how long until you're down to 20%. Well, class, half-life was 50%, which was 0.5 or 1/2 that we used. So, if they tell us 20%, how do you write 20% as a decimal or a reduced fraction? Yeah, good. 0.2, I heard them both actually, or 1/5. So if someone says to you, how long until 20% of the original amount remains, you would go ln of 0.2 divided by negative 0.0241. Still using that same percent, it's still a decay. What was this? Was this years? But this was years, wasn't it? Yes, it was years. Okay. Now we're going to figure out how much there is until 20% is left. Anyone new? Want to try out your calculator skills? Let me know. Someone either in the back right or the front left up here? No, we'll make fun of you if you're wrong. I'll just ask you to try again. You want to try? 66.78. You're a genius. Nice job. You got it. Well done. Okay. We can do this. We can do this, but here's the trick question they ask you, and this is the annoying one. If they say how long until 75% is gone, they are asking us a trick question. Because the way these equations are set up, what we need to know is we need to know how much remains. So unfortunately, as soon as I see that 75%, I get so jazzed that I'm like, oh, I must do this. ln of 0.75 or ln of 3/4, doesn't matter which one because I'm so smart. But unfortunately, these will not give you the right answer because they're messing with us. Because the way these are set up is we need to know how much is remaining. So if 75% is gone, how much is remaining? 25% or 1/4. So really what we needed to do is one of those. Because these are set up not to figure out how much has been lost, but how much remains. And that can be very, very frustrating. Because you can go nuts thinking, I am typing in the right number, why is I not getting the right answer? It's because you might be typing in how much is gone, not how much remains. And that didn't come up with half-life, because if half is gone, half remains, so you don't really even need to know what that half means. But it turns out it means how much remains, not how much is gone. What do we get here? $57.52 years. Good. Well done. All right. Let's look at a homework problem. I'm sorry. Questions, comments? You okay? All right. I pulled this one straight from the homework. You might have a similar problem with different numbers, but I pulled this one straight from the homework in 4.6. So this is 4.6 number 4 for me. if 14 grams of a radioactive substance are present initially and 3 years later only 7 grams remain, how much of the substance to the nearest tenth of a gram will be present after 4 years? This is a great example of a where do I begin problem. Where do we begin with almost every problem? In this section, you begin like this. That's how you begin, using the one formula that we use in this section. And then you just start figuring out what you know. 14 grams are present initially. Does that sound like a starting amount to everyone? Okay. E is just E. 3 years later, only 7 grams remain. 3 years later, 7 grams remain. They're giving me 2 pieces of information there. What do we get? What are they giving me? Time.
Time and starting amount.
And decay.
They're not giving me the K yet, but they're giving me the time, and they're giving me the ending amount. Does everyone see how I'm getting that information just from that first part there? 14 grams to start with, 3 years later, 7 grams remain. Okay, so what is the only thing I don't know here? K. I think I'll solve this for K. Because it is not given. I'm going to solve that for K because K is not given in the problem. Oh, this is interesting. 7 divided by 14 is 1/2. E to the 3 times K. What do I do now?
ln.
ln of both sides. What does the right-hand side simplify to?
3K.
3K. Divide both sides by 3, I guess. Let's get our K. Let's get our K. I did K to 3 decimal places, everyone. Don't freak out if you're getting a negative answer, everyone, because we're not doing an amount of time right now. This is not an amount of time.
This is the decay rate.
This is a decay rate. So should it be negative?
Yes.
Yeah, it should be negative because this is a decay rate we're looking for. I heard some mumbles, so I thought I'd take care of that. Yeah, this is a decay rate. And what are we getting? Negative?
0.231.
Negative 231. Good. Yeah, it actually looks a lot like half-life. So you might have been thinking, am I looking for a half-life right now? No, we're actually not. But it's not a coincidence because it turns out, everyone, that half-life looks like this. That's what half-life looks like. But check it out. If you multiply both sides of this by K, you get KT equals ln of 1/2. Then if you divide both sides by T, you get K equals ln 1/2 over T. So it's not a coincidence that it looks like that. It's very closely related to a half-life. It's just that instead of knowing the time, instead of knowing the K and finding the time, we know the time and we're finding the K. What the heck am I supposed to do with this? I don't even remember what this problem was. How much of the substance to the nearest tenth of a gram will be present after 4 years? When in doubt, go back to the beginning. All right. The question asks, how much of the substance to the nearest tenth of a gram will be present after 4 years? How much of the substance will be remaining after 4 years? So I need to know what P of T is. Do I still know how much I started with originally in the very beginning?
Yeah.
How much did I start with in the very beginning? 14. Do I know what K is now?
Yeah.
Yeah.
Yes, I do. And it wants to know how much I have after 4 years. Hot damn. Do I know how to plug that into my calculator?
Yes.
Yes, I do. So excited about math.
Zero.
And we're supposed to round this to the nearest tenth. Don't be shy. If you think you got it, tell me.
5.6 grams.
5.6 grams. Nice job. Now, I need to caution you all of you on this problem because that is the right answer. And when I did this problem, this is how I did it. I plugged in that answer, and I got it right, and I'm a winner, and you can too.
Mistake, I didn't forget the-
But here's the big issue with this problem. It actually told us not to round until the final answer. And we did round. And I told you to round, so that's on me. I told you to round this to 3 decimal places, didn't I? So it is possible we could have gotten the wrong answer. So really what we should have done is we should have kept the exact value of K
That was the exact value.
and used it here. Well, the problem is we don't know the exact value. It was in our calculator.
Oh, yeah, you're right.
So what happens is when we did this ln of 1/2 over 3, our calculator was holding on to the exact value.
So the rest of the.
And then that should have been what we plugged in here. Now, I had us go to 3 decimal places because I knew that would be enough because I knew we were rounding to the nearest tenth when we were done. But technically, when you're doing a problem like this, any problem that involves rounding, every time you round, you lose accuracy. So what you really want to do, if you can avoid it, is you really never want to round until the very last step. In previous semesters, I've gotten a lot of emails from people doing the homework in this section, and most of the time, people know exactly what they're doing. They just have a rounding error. So watch out for that. Let's do one more story problem here. I like this one because it looks so much worse than it is. This one looks so much worse than it is. Suppose an Egyptian mummy is discovered in which the amount of carbon-14 present is only about 1/3 the amount found in living human beings. The amount of carbon-14 present in animal bones after 2 years is given by, well, that's cordial of them. They give me an equation to use. Maybe that will help me solve this problem. Where y sub 0 is the starting amount of carbon-14 present in living human beings. About how long ago did the Egyptian die? This is terrible. But there's a very key piece of information up there that's going to help us solve this problem, lickety-split.
The 1/3, isn't it?
That's it, right there. One-third, right there. Take a quick moment. Does it say 1/3 is gone or 1/3 remains?
Right.
Remains.
It says 1/3 remains. So really what we're going to do here is a 1/3 life, not a half-life. And if we're doing a 1/3 life, we don't write ln of 1/2, we write ln of 1/3. And what do we divide that by?
The decay rate.
The decay rate. Decay rate is already a decimal.
I was already given to me.
It is fine how it is. When they give it to us as a percent, we got to convert it. But they are already giving us the decimal, so we can just do it just as it is. You do not need to change it. You just got to make sure you put the right number of zeros in your calculator. So we're doing ln of 1/3, and then we're going to divide that by negative 0.00012116. And we are going to round to the nearest year. Give everyone a chance before anyone shouts out the answer. Give everyone a chance before anyone shouts out the answer. Anyone on the back left table here want to give it to me? Any of you got it? 9,035 years. What do we think?
Yeah.
I think she's right too. Nice job. So, I will go back to my statement that I made to all of you before in the past. Are story problems really harder than regular problems? Not necessarily, you just need to figure out what they're asking you to do. This long, nasty paragraph had two important pieces of information for us in it. It had that 1/3 in it, and it had that number right there. Those are the only two things we needed to solve this problem. And we reached for the calculator and we solved it. So you do not want to let these freak you out. I did this one to show you that intimidating story problems don't have to be that bad. I did this one because I actually think this one is hard. This one had a lot of steps. And it's very, very easy to get lost when you're doing this one. There was a lot going on in here. But at the heart of every homework problem you're going to do in this section, just remember, if it is a 4.6 problem and you are lost, think about how that comes into play. Think about how that comes into play, because that's the big equation in this section. All right, how's everyone doing? Okay. Listen very, very carefully when I say next. Not graded, yours to keep. You don't need to turn it in. Pop quiz. Rachel, can you pass out a couple of these for me? Thank you. There you go, there's a bunch.
No way that was red.
You know, our test 1 week from today is going to have inverses on it. And we haven't done inverses in a while, so we better make sure we're cool. So we got one here and one here. Okay. All right, everyone, go ahead and get started on that. We'll work on it for the rest of class. You can finish it when you get home, and I'll post the answer key on D2L. Sound okay? Get started.